Hello and welcome to Lesson 2 of GCSE Quantitative Chemistry with Mrs Castanera. This lesson today is called Conservation of Mass, and we're going to start with our keywords, which are mole, relative atomic mass, relative molecular mass, grams, balanced equation, and you're going to need a highlighter to highlight those. So once again, for this lesson, you are going to need your periodic table of the elements, okay, to help you with the lesson content. So our first thing that we're going to be doing is you're going to pause the video whilst you complete the knowledge check. Please pause the video now. Okay, so let's go through those. Write the symbol for relative atomic mass. Well, that is a capital A with a subscript R. And if you recall, subscript means it's written slightly below the same letter A. So down here, not AR like this. That is incorrect. So if you've done that, that is wrong. That is the chemical symbol for argon, another thing entirely. You need to have written it like this, where the R starts below the A. Question 2. Name the subatomic particles used to calculate atomic mass. That would be protons and neutrons. Remember, if you've made any mistakes, please correct them in a different colour to the pen that you used to answer the questions. Question 3. Give the units used to measure mass. So that's grams or lowercase g. Give the value of a mole. Okay, so this is a higher tier question only. So if you're a foundation student, don't worry about answering this question. So if you are a higher tier student, your answer should be in 6.02 times 10 to the power of 23 atoms. Or I would also accept 6 times 10 to the 23 atoms. And you can't just say this number, you need to say the atoms part as well, okay? Otherwise, we don't know what we're talking about. Question 5. Name the subatomic particles found in the nucleus. Well, they are protons and neutrons, and you'll need both of those to get the answer correct. Question 6. Give the units for percentage mass. Well, that would be percent. Question 7. Write the symbol for relative molecular mass. So that's a capital M with a lowercase subscript r, once again. So a reminder of how that looks. That's a capital M and the R must be lowercase and it must start below the M. Okay. Again, if you've written it like Mr., that would be wrong. Okay. Question 8. Define a compound. Well, it's two or more atoms chemically bonded together. Okay, so write out any corrections. Give yourself a mark out of 8 if you're a higher tier student and a mark out of 7 if you're a foundation tier student. Then we're going to move on to our lesson. So this is today's lesson. An overview of what we'll be doing is that we're going to explain the meaning of conservation of mass. So we did briefly touch on this last lesson. We're going to go into this in more detail this lesson. We're going to calculate relative atomic mass. Again, we looked at this last lesson, but we're going to review it in more detail this lesson. And lastly, we're going to balance simple equations, something we have done before, but we will have more practice at that today. So, the law of conservation of mass. So we wrote this out on our notes page in the first lesson, okay, and this is quite a lengthy explanation of the same thing. So to conserve originates from Latin words con, meaning together, and servare, meaning to keep. For us, it means to keep the same. The law of conservation of mass states that no atoms are lost or made during a chemical reaction. So, therefore, the mass of the products must equal the mass of the reactants. I'm going to highlight this key law. So basically, they're kept the same. There's a sort of missed letter there. They are kept the same. In simple terms, chemistry is just the rearrangement of atoms or molecules into new products by breaking bonds and reforming them again. And these are called reactions. In order to make products, we must start with the correct quantity of atoms of the reactants in order to end with, so that we can end up with the correct products. We can't just add extra atoms from nowhere. They're not going to magically appear. And we can't just make them disappear either. We can't just make things appear or disappear from nothing. Okay. So it's important to remember that there are usually trillions of atoms and molecules colliding with each other in reactions, even though the chemical reactions or chemical equations only show some of these. Okay, so it asks you that with your teacher's support on the notes page, explain why some reactions the mass of the substances appears to increase and why in some reactions the mass of substances appears to decrease. Okay, so we are going to move on to our notes page, which is page 19. Okay, now let's consider a reaction. So we're going to look at the reaction of calcium carbonate and how it turns into two new products. So I'd like you all to write this out. Now, calcium carbonate can turn into calcium oxide and carbon dioxide. Okay, so calcium carbonate, there's a formula for this, CaCO3, calcium oxide is CaO, and carbon dioxide is CO2. So this is a balanced equation. We're not going to worry too much about that for now, but this is a balanced equation. And we know that because the number of elements shown here is exactly the same as the number of elements on the reactants, on the product side. So number of reactants is equal to the number of products. However, when we do this experiment in real life, that's not what it seems. So the way that this reaction occurs is typically we will have a heat source. Okay, and we'll have our lump of calcium carbonate inside a boiling tube. Okay, like so. And our boiling tube will be heated. Okay, so we'll label it. So we could weigh this calcium carbonate before our experiment. Okay, and then after our experiment, we can weigh it again. And the problem's going to be that the calcium carbonate will have turned into calcium oxide. So we now have some calcium oxide. And what will have come out of the top here is carbon dioxide, because it is a gas. Okay, so we've got our solid calcium carbonate, we heat it, we are left with solid calcium oxide and carbon dioxide gas, which has escaped. So we re-weigh this afterwards, it has lost mass. Okay, I'm going to write a sentence to explain this. Okay, so this experiment appears to lose mass as carbon dioxide, a product, is lost to the surroundings. So how could we prevent this from happening? How could we make it so that the products weigh exactly the same as the reactants? Well, we would have to trap the carbon dioxide gas, and we would have to then include that trapped carbon dioxide gas in our weight at the end of the experiment. If we did that, we would find out that actually the reactants and the products are exactly the same mass. Okay, so I want you to make sure you've got all of that written out on your student notes page, please. If you haven't, please pause the video whilst you do that. Okay, so I have ruled off below that, and now I'm going to talk about the opposite problem. Okay, so we're going to zoom in again. Now this time we have a reaction that gains mass. When we react magnesium with oxygen, we produce magnesium oxide. Okay, so let's put our symbols for this. Magnesium, which is a solid, oxygen, which is O2, which is a gas, turns into magnesium oxide, which I really should have done in a straight line, which is MgO, which is a solid. Now, similar problem this time. The oxygen is a gas. It comes from the surroundings, okay? So it's not taken into account in our original weighing. So we'll weigh this magnesium and say the magnesium weighs 48 grams, okay? So we have 48 grams of magnesium plus an unknown amount of oxygen, which will turn into 80 grams of magnesium oxide. So how much oxygen did we take in from the atmosphere? Well, we can work that out because 80 take away 48 is 32 grams. So we know that to produce this 80 grams of magnesium oxide, given that with the law of conservation of mass, given that the reactants and the products must be the same mass. So we know that if the oxygen was 32 grams, the magnesium was 48 grams, that makes 80 grams. So we know that we've taken in 32 grams of oxygen from the surroundings to react with our magnesium and turn it into magnesium oxide. Okay, we're going to write some notes about that now. Okay, so this experiment appears to gain mass as oxygen, a reactant, is taken in from the surroundings. Okay, so I'd like you to make sure that you've got all that written down. Pause the video if you need to do that now, and then we can move back on. Okay, so where were we? We're here. So we're going to write C, page 19 for notes. Okay, and we're going to just add in a little note up top here. Okay, so we're going to summarise the law of conservation of mass. So mass of reactants is equal to the mass of the products. Okay, so the mass you have before the reaction starts is going to be equal to the mass you have after. That is the law. That is the law of conservation of mass. That is the most important thing to remember from this. Okay, so make sure you've got that down, and then we're going to move on. So unfortunately, we can't do the learning activity as it's a practical, and we cannot do that outside of the lab. Okay, so that will be done at another time when we're in school and we're able to use the labs. Okay, so we'll move on now to page 16. Balancing equations. So chemical reactions can be represented by symbol equations, which are balanced in terms of numbers of atoms of each element involved on both sides of the equation. For example, water can be produced from the reaction of hydrogen gas and oxygen gas, both of which are diatomic molecules, which means they're made of only 2 atoms. I'm going to highlight this because that's quite an important thing to know. It's useful to know. So we have here our oxygen plus hydrogen turns into water. So this is our equation here. And then we have our chemical symbols. So O2 H2 and H2O. So if you've got other colours of highlighter or colouring pens, you can follow along and do this with me. I like to use a bit of colour for this. So these two circles here below oxygen represent the oxygen atoms. So I'm colouring them in pink. Okay. Then we have two hydrogen atoms, which are represented as black. And then when we have water, these are the atoms in water. Two hydrogens and one oxygen. Now, to check if it's balanced, we need to find the arrow. Okay. And I strongly recommend drawing a nice, obvious line between the two. Okay. So, this is the reactants and this is the products. I'd like you to label that too. Now, remembering our law of conservation of mass, there must be the same amount of atoms before the reaction as after the reaction. So let's check. Before the reaction, we have two oxygen atoms. After the reaction, we have only one. That means it is not balanced. Before the reaction, we have two hydrogen atoms. After the reaction, we have two. So that's good, but we have a problem there with the oxygen. So to make sure that there are two oxygens after the reaction, we need to add a 2 in front of this. So that's exactly what we've done here. Okay, and so now on the right hand side we have two of our oxygen molecules, which is great. We've got 2 before, so that is balanced. And now we have 1, 2, 3, 4 hydrogen molecules. So to balance that, to make sure we've got 4 before, we need to add a 2 here in front of our hydrogen to make sure we have 1, 2, 3, 4. So let's double check that. 2 oxygens before, 2 oxygens after. Good. 4 hydrogen atoms before and 4 hydrogen atoms after. Perfect. That is a balanced equation. Okay, so that's all that balancing equations is about. Now, there's a YouTube video here that I want you to watch because it's very useful and quite helpful about balancing equations. So, if you've got a digital copy of this, which you all should, you'll be able to click on this link. Alternatively, type this into the search bar, into your browser, and you'll be able to go straight to the video. So, you might want to make some notes on your student notes page or another piece of paper. I highly recommend it. And then we're going to work through this together. Okay, so pause the video whilst you watch that. Okay, so now that we've watched the video, we're going to complete the equations below by balancing them. There are some hints here that are going to help us. Remember the law of conservation of mass, okay? Atoms are not created or destroyed, so you need to have the same quantity each side of the arrow. Okay, you can't change or delete or add to the subscript numbers, okay? Subscript numbers are, for example, this little 2, that is a subscript number. You can't change that. That means that the atom goes around as a pair always. Now, you can only place large numbers in front of the reactant or the product, not the subscript numbers. Okay, so rather like we did before, we added a 2 in front of our hydrogens and a 2 in front of our H2O's, waters. There isn't always a best place to start. Just pick something, one of the reactants or products, and make it balance. And you just keep doing that. Once you've balanced one reactant or product, review the equation again, as it will almost always change something else. Okay, keep reviewing and checking. The balancing numbers aren't always 1, 2, or 3. They can actually be bigger than this. When dealing with brackets, the subscript number applies to everything inside the bracket. So, for example, OH in brackets with a small 2 after it means that there are 2 OHs that we're talking about there. There's 2 lots of OH. Okay, so it's 2 H's and 2 O's. Right, so now that you've got all that done, I'd like you to have a go at these equations, have a go at balancing them, Okay, and we'll see how we do and we'll go through it and I'll explain how it's done. But pause the video whilst you try and do this. Okay, so let's go through those. I'm going to explain the first few in case you've gotten stuck and you're not sure how to carry on. So N2 plus H2 turns into NH3. So here we have our nitrogen atoms, okay, two little circles here. And then we have our hydrogen atoms, which I'm going to make yellow. And then over here we have NH3, so we've got our nitrogen in the middle, which is blue, and 3 hydrogens around it. Is this balanced? No, definitely not, because there's only one of the blue atoms after the arrow. Okay, and there are 3 of the yellow ones, which is too many. Okay, so we need to make this balance more. First of all, let's start with the blue. So there's 2 before, but only 1 after. So we can draw another one. So let's do that. Now we've got the right number of nitrogens, the blue atom, before and after the equation. So the nitrogen's balanced. Let's now consider the hydrogen, because we're checking it. So there's 2 before, and then afterwards there's a lot more than 2. 1, 2, 3, 4, 5, 6. So we need to make it so that there is 6 hydrogen molecules, or atoms even, before reactants. So now we have 6 hydrogen atoms before the reaction occurs, and we have 6 hydrogen atoms after the reaction occurs. Let's double check we've still got nitrogen in a good situation. So 2 lots of nitrogen atoms before the reaction and 2 lots of nitrogen after the reaction. So hurrah, that is balanced, but we haven't turned that into a change for our equations. So let's have a look. So I now have 1 lot of N2, so that's the same. I have 1, 2, 3 lots of H2, so I've drawn them as they're shown, and I have 2 lots of NH3. So that is now balanced. So the correct answer for the first one was N2, 3H2, 2NH3. Well done. Now, if you had a look at that because you were really stuck, please carry on with the rest of them. Pause the video now if necessary if you haven't completed them all. Okay, so let's move on to the next one. We'll go through that just the same as before. So this time we have 2 hydrogens, and again they're diatomic, which means they go around in a pair. And we have 2 oxygens, because it's diatomic, it goes around in a pair. Then we have our arrow, which tells us now we have our products, and our products are H2O, like this. Now let's make this make more sense. We'll have our oxygens as pink, and our hydrogens once again as yellows. Ordinarily in chemistry we'd use different colours, but I'm not going to worry about that for now. So 2 hydrogens before, 2 hydrogens after. That's brilliant, wonderful. 2 oxygens before, but only 1 oxygen after. So we can't half this. Okay, we don't do that. We have to double this. So let's do another another H2O. Okay, well, that's good because now we have 2 oxygen atoms beforehand and we have 2 oxygen atoms after. So our oxygen atoms are good. Now let's consider our hydrogens. We have 2 hydrogen atoms beforehand, but we now have 4 afterwards. So we need to add more hydrogens to our products beforehand, to our reactants before the reaction occurs. So let's check that. 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 hydrogens. That's good. The same before and after. 1, 2 oxygens before. 1, 2 oxygens after. Excellent. So now we've got the picture balance. Let's change this in the actual equation. So we have 2 lots of H2 here. Okay, that's the same. And then we have 2 lots of H2O. So now that is a balanced equation. So there is our answer for the second equation. 2 hydrogens plus O2 turns into 2 H2O. Okay, so we can carry on with this, okay, and I'm just going to go through the next one. Okay, so here we have 1 phosphorus atom, one diatomic oxygen, so that's 2 oxygens, and then our product, which I haven't drawn, I've just done them as circles because we're not sure exactly how this goes together at GCSE. So P2 plus 5 oxygens. Okay, now this is definitely not balanced. There's a lot more atoms in the products than there are in the reactants. So first things first, there are 2 phosphoruses here, so we need to have a second one here. Wonderful. Then there are 5 oxygen atoms here and only 2 here. Now we can keep adding to this, but we can only get 4 or 6 because unfortunately you can't have 2.5 diatomic oxygens. It doesn't work like that. So we need to know what number can we get 5 and 2 into. Well, in this case, we're now over the amount because we couldn't make it correct. So we now have to do another one of these. Okay, so now we've got 10 oxygen atoms. Well, 10 is a number that can be created on the left side as well. So now we've gone all the way up to 10. So 2, 4, 6, 8, 10 oxygens before, and 2, 4, 6, 8, 10 oxygens after. Although now we have 4 phosphorus after, so we will need to draw 2 more. Okay, so let's finally do another check on that. So 1, 2, 3, 4 purple phosphorus atoms before, and 4 purple phosphorus atoms after. 2, 4, 6, 8, 10 oxygen atoms before, and 2, 4, 6, 8, 10 oxygen atoms after. So that is balanced. Now let's make sure that this is now represented in the numbers up here. So there are 1, 2, 3, 4 phosphorus atoms. There are 1, 2, 3, 4, 5 diatomic oxygens, and there are 2 lots of P2O5. Now that was a tricky one, okay? If you're not sure how we got there, watch it again and see if that helps. Okay, and lastly, we're going to be doing S8 plus O2 turns into SO3. So let's draw that. Okay, so you can already see the problem here. We have 8 sulfur atoms to start with. Then we have 2 oxygen atoms, and the whole thing turns into this. Now you can see that there is only 1 green sulfur atom on this side of the equation, the products, and there are 8 of them here. So the first thing we need to do is do 8 of these and see where we end up. So let's do that. So now see we have quite a lot more oxygens after than we have before. So let's count them. 3, 6, 9, 12, 15, 18, 21, 24. So there are 24 oxygens this side. Okay, and you can write that down. Okay, so we've got 24 oxygens. If you need to write that down, you can. So to make 24 this side, we will need 12 of our diatomic oxygen molecules. So let's draw that. Okay, so as you can see, we now have 24 oxygens this side. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And again, we can write that down. So we've got 24 oxygens on both sides. Great. Now let's double check our sulfurs are still correct. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So what we can say now is that we have definitely balanced our equation because the reactants are exactly the same in number as the products. So let's turn this into numbers in our equation. So S8, that's exactly as it started. Now we have 12 lots of oxygen here. So 12 lots of O2, 12 diatomic oxygens, that's 12. And here we have 1, 2, 3, 4, 5, 6, 7, 8 lots of sulfur trioxide. Okay. So again, that was a bit tricky, but if you got that correct, well done. There's more ways to do this than I've shown you here, and some of you will have worked out that you can do this mathematically. So now that we've gone through all of those, there's an extension activity, well, it's not extension activity, a continuation of this exercise. Okay, all of these, all the way through to here until we get to the section for higher tier students. So I want you to have a go at doing this yourself. I won't go through these in the same way, okay? I will just give you the answers for these. So feel free to use the method I've shown you to work through those. Okay, so let's go through those. First one is 2 NaCl plus F2 turns into 2 NaF plus Cl2. So you need both of those to be correct to get the mark. Do any corrections in a different coloured pen, please, to show where you've made mistakes and where you've gone wrong. Next question, you need to put a 2 in front of the O2 and a 2 in front of H2O to balance the equation. Next question, you need to put a 5 in front of the O2, a 3 in front of CO2 and a 4 in front of H2O. That was a trickier one. This one was probably the hardest one of the lot, or at least one of the hardest. So you need to put a 2 in front of this one, 25 in front of the oxygens, 16 in front of CO2 and 18 in front of H2O. That one was difficult because just the large quantities involved. Okay, next question. You need to put 2 in front of the Na, 2 in front of the H2O and a 2 in front of NaOH. And you do need to get all of those to get the mark. Next question, you did a 6 in front of O2, a 6 in front of H2O and a 6 in front of CO2. Okay, so let's go through the next section. Okay, so you need to put a 2 in front of Ag2O, then a 4 in front of Ag to get the mark. Next question, you need a 2 in front of the KClO3 and a 2 in front of KCl and a 3 in front of O2. Let's move on to the next section. Here you need a 2 in front of PbOH2, a 4 in front of HCl, a 4 in front of H2O and a 2 in front of PbCl2. Next question. So this time you needed a 3 in front of NaOH, a 3 in front of NaCl. So there we go. Next question. You needed a 2 in front of the AlBr3, you needed a 3 in front of K2SO4, a 6 in front of KBr, and this one stays as it is. That was another very tricky one. Okay, so if you're a foundation tier student, this next section is higher tier only, so you can move on to the knowledge check and you'll need to fast forward to that. So you can do the knowledge check and then go through the answers. Okay, if you are a higher tier student, we'll go through the rest of this lesson before we move on to the knowledge check. So, the importance of balancing equations. So a balanced equation shows the correct quantity of each atom or molecule required to satisfy the law of conservation of mass. In fact, the balanced equation can act like a ratio which can be used by chemists to calculate the proportion of chemicals needed at the start of the reaction, which is very useful for a company that doesn't want to waste profits on unnecessary reactions. So, balanced equation can act like a ratio which is used to calculate the proportion of chemicals needed at the start of a reaction. Okay, it prevents the wasting of profits. Okay, because of it stops us wasting unnecessary reactants. So, in this example below, which is shown here at the bottom of the page, on page 17, in the example below, a chemist would need twice as much hydrogen compared to oxygen to make water. In fact, we could say that for every mole of oxygen, we need twice as many moles of hydrogen. A chemist could use the balanced equation and the relative molecular mass to calculate the mass of each molecule needed in the reaction. And this is quite an important concept, something that you might be asked to do in the exams. So, here we have our equation, which is O2 plus 2H2 turns into H2O. The ratio is 1 lot of O2 to 2 lots of H2, gives us 2 lots of H2O. And you can see that here in our reaction. So we've got 2 atoms of oxygen, 2 atoms of oxygen, which I'm colouring in pink, 2 lots of hydrogen, well actually it's 4 hydrogen atoms, and then we produce 2 water molecules. Okay, now the relative molecular mass of oxygen is 32, 16 each for each oxygen atom, and the relative molecular mass of hydrogen is 2 lots of 2, which makes 4, and the relative molecular mass of water is 18 when we add it all together. Okay, be aware that this is not quite correct because it's 1 plus 16 plus 1, not 161. Okay, so our mass is the relative molecular mass multiplied by the moles. So 32 times 1 gives us 32 grams of oxygen required. 2 lots, because the ratio is 2 multiplied by 4, gives us 8 grams of hydrogen required. And the ratio of 2 multiplied by the molecular mass of 18 gives us 36 grams of water. So we now know that we require 32 grams of oxygen for every 8 grams of hydrogen, which will produce together 36 grams of water. And so that prevents us wasting and putting in too many of either of these. And what people might be tempted to do is put too much hydrogen in, because it looks like you need a lot more hydrogen. But remembering that the molecular mass of hydrogen is very low, we actually only need 8 grams of it, even though we need twice as many hydrogen atoms. Okay, so what we're going to do now is we're going to move on to the knowledge and application check on page 18. Okay, so regardless if you're foundation tier or higher tier. However, there are a couple of questions that are higher tier content. So question 7 is a higher tier question. So if you're a foundation student, don't worry about question 7. And also question 12, and yes, we have run out of numbers again, so you will need to write them in. So question 12. So pause the video whilst you do that, and then we'll go through them together. Okay, so let's review those questions. Question 1, write the symbol for relative molecular mass. So that is a capital M and a subscript lowercase r, not Mr, as I've explained already. Give the units used to measure mass, so that's grams, or a lowercase g. Make sure you're marking in a different coloured pen and that you add any corrections that you need. Question 3, name the subatomic particles used to calculate atomic mass. That would be protons and neutrons. You need both of them for the mark. Question 4, name the subatomic particles found in the nucleus. Again, that's protons and neutrons. Question 5, write the symbol for relative atomic mass. Well, that is capital A, lowercase and subscript r. Question 6, define compound. It's 2 or more atoms chemically bonded together. Question 7, a higher tier question. Give the value of Avogadro's constant, so it's 6.02 times 10 to the 23 atoms. You must say the phrase atoms afterwards. If you've written 6 times 10 to the power 23, that is also acceptable. Question 8, and that was a higher tier answer. Question 8, give the units for percentage mass. Well, that would be percentage. Question 9, define the law of conservation of mass. So, is there anything that says the mass of the products is equal to the mass of the reactants? So I've just written the mass of the products must equal the mass of the reactants. Or you can say is equal to the mass of the reactants. Question 10, suggest why the mass of reaction can appear to reduce. Well, if gas is given off into the surroundings, then it appears to get lighter and the mass reduces, or looks like it's reduced. Question 11, calculate the mass of magnesium oxide formed from 24 grams of magnesium and 32 grams of oxygen. Okay, so 24 grams of magnesium is 1 mole, 32 grams of oxygen is 2 moles. Okay, so you'll get a mark for doing both of these, so mark for each. Then you can only react 1 mole of magnesium with 1 mole of oxygen, okay, which is going to give you 24 plus 16 to give you 40 grams, and you'll have 1 mole of oxygen left over. Okay, so it's going to produce 40 grams. So there's 3 marks there, okay, so I'm going to put that in brackets 3. Question 12, nitrogen reacts with hydrogen to form ammonia. Calculate the mass of nitrogen required to form 68 grams of ammonia when using 12 grams of hydrogen. This is a very tricky, higher tier question. Okay, so first of all, you need to know that the chemical formula for ammonia is NH3. Okay, that's not actually worth a mark, but you do need to know that to be able to do the next calculation. To work out the relative molecular mass of ammonia, it's 14 for the nitrogen and 3, that's 1 each for the hydrogens, gives us 17, so you have a mark for that. Now, the number of moles is the mass divided by the relative molecular mass, so you can have a mark not for writing that out, but for putting numbers in. So 68 grams, which is the mass of nitrogen, divided by 17. Okay, so you get a mark for doing that part and a mark for coming up with the answer of 4 moles. There's 3 marks so far. Now, the mass of nitrogen required is going to be 4 moles multiplied by 14 grams per mole to give us 56 grams. Okay, so 1, 2, 3, 4 marks available here. Give yourself a mark out of 4. And the last question looks like a higher tier question, would probably only be given to higher tier students. However, there is a chance it could be given as a foundation tier question, although it isn't particularly likely. It's a trick question. They're trying to trick you. Okay, you could calculate it this long way around in a very similar way, but actually using the law of conservation of mass, it's really, really easy. Okay, because we know that calcium carbonate that decomposes, okay, is going to lose carbon dioxide and leave calcium oxide behind. So this is the calcium carbonate amount. Take away the calcium oxide, then that gives you the number of grams, the mass of carbon dioxide lost. So it's a trick question, okay, because this is the reactant and these two are the products and they must add up to the same mass as the reactants. So the answer is 44 grams, okay, and there's only 1 mark for that. Okay, so if you're a higher tier student, give yourself a mark out of 18. And if you are a foundation student, give yourself a mark out of 13. Okay. So if you've got more than 10 in this as a foundation student, you've done exceptionally well. Okay. If you've got more than 6, then you've done very well still. If you're a higher tier student and you've got more than 8, you've done very well. If you've got more than 13, then you've done very well, because this is some very tricky questions here, okay? You've done exceptionally well if you've got more than 13 or 14. So that concludes our lesson. If you have any questions, please feel free to speak with your teacher, email them, and they'll be very happy to help you.